Alright, let's finish up the section by talking about irreducible and indecomposable representations. So if we have a representation rho of G on a vector space V over C, of course this is always over C, then we say that rho is irreducible if for every single G-stable subspace, either that subspace is going to be 0, meaning it consists only of the 0 vector. So I guess we could, if we wanted to be super technical, we could put this in brackets specifying that this is the set consisting of just the 0 vector, but whatever. Or it's V. So if you have a G-stable subspace, it's either like the smallest subspace possible or the whole thing. This is sort of like simplicity with groups, except that it's not. So that's irreducibility, but we say that rho is indecomposable if whenever we write V as V1 direct sum with V2, then one of these two is going to be the entire vector space. And it sort of feels like at first that these should be the same thing, but they're not. So let's discuss that. So let's take an example. We have Sn acting on Cn. We've discussed this before. This is not irreducible because we have a stable subspace, and we talked about this before, and it's the span of this vector, the sum from 1 through n of ei, where the ei's form a basis for Cn. And basically what we showed is that when you act on this vector by an element of Sn, you're just permuting the ei's. In the sense this is just the sum of them, and because addition is abelian, it doesn't change anything, and so this is G stable. But this span is it's the span of one vector, so it's one dimensional, and in particular it's not 0 dimensional and it's not n dimensional. Okay, so I guess sure you have to say n is greater than 1 if you want to be really fussy about it, but yeah, so this is not irreducible when n is strictly greater than 1. Okay, so what is the relation between irreducibility and indecomposability? So irreducibility implies in the other one, but the reverse is not necessarily true. So the first statement is clear. So the reason it's clear is because for every subspace, either it's 0, let's suppose it's irreducible. For every subspace that's G-stable, either it's 0 or it's the whole space. So suppose that we can write V as V1 direct sum with V2. Then each of these two things by irreducibility has to be either 0 or the whole space. It could be, so the dimension of these, the dimension of these two things have to add up to the dimension of this. And let's assume that if the dimension is 0, then both of these things are 0, and so it's automatically indecomposable. If it's greater than 0, then this has dimension greater than 0, and it can't be the case that both of these have dimension equal to 0, because then the dimension of this thing would be 0, which would contradict the equality. Therefore, at least one of these things has to be non-zero. But if it's non-zero, then it's the whole thing. And so one of them is the whole thing. And so there you go. So that's why that implication holds. And so let's look for a counterexample to the reverse. And for here we have to look at representations on infinite groups. So it's a little weird, and it's not something that you might see in a first course on representation theory, but it's easy enough to present that we'll go ahead and do it. Because I mean, like it's Jean-Pierre Serre has representations of finite groups, not representations of groups. Okay, well, linear representations of finite groups, whatever. Anyways, so we let rho be a representation of Z on GLC2, and it's given by rho sub n is this matrix. Is this in GLC2? Well, if you take the determinant's 1, so that's good. Is this a bijective map from C2 to C2? It should be. I'll leave that to you to check. Is that super easy to check? It should be. What's the kernel of this thing? The kernel. Well, actually, sure. Let's go ahead and let's compute how this acts on anything. So if you have 1, 0, and 1, A, B, this is going to be A plus Bn, and then we're going to get B on the bottom. Okay, so let's suppose that we plug something in here and we get the 0 vector. So what does that mean? Well, certainly B has to be 0, and if B is 0, then A is 0. And so the kernel consists only of the 0 vector. Okay, so this matrix is injective, and certainly it's it's invertible. The determinant is non-zero, so it's invertible, and so it's automatically bijective, and it's going to be a group homomorphism because if you compose two things, let's do this really quick. 1M01, 1. So composing these two maps gives us a new map. That's just, it's going to be 1 n plus m01. And that's exactly what we need for it to be a group homomorphism. So yeah, this all works out. Okay, so moving on. So what we're going to do is we're going to find a z-stable subspace. So for every single integer n and complex number z, if we look what happens to the vector z0, so it's just this matrix being applied to z0, and you multiply it out, it's just z0. So not only is it stable, but it actually it fixes every single vector in here, and so this is a z-stable subspace because acting by rho n on this will fix it. Obviously, this is a subspace because it's got 0. It's closed under addition and scalar multiplication. So it's a z-stable subspace of C2, and it's non-trivial because it's just the span of one vector. So it's got dimension 1, which is neither 0 nor 2. That's what I mean by non-trivial. I mean that's not the 0 subspace, and it's not all of C2. All right, so this means that rho is not irreducible, which is not to be confused with reducible, which in math is not something you want to do. If like irreducible is a technical term and something does not have this property, you don't want to just drop the ir part off of it. That's just it's like you've got to be really careful with words in math, and so saying that something is not having this property is how you want to say it, because if you change this, if you replace irreducible, if you replace not irreducible with reducible, then maybe reducible has its own separate special meaning that you don't know about, and then you're saying something that might not even make sense. Anyways, so rho is not irreducible. So it's not irreducible, but we're going to show that it is indecomposable. So So it can't be the case that indecomposable implies irreducible if we have an example of something which is indecomposable but not irreducible. Okay, so let's assume for contradiction, that's what AFC is, that rho is not indecomposable. Again, that's not, it doesn't mean it's composable, doesn't mean it's plastic. It means, wait. I really botched that. So it's not indecomposable. So there must be some, okay, so if it's not indecomposable, then it's not the case that whenever you break it up as a direct sum, then one of them must be the whole space. So if we just do a dimension argument, the vector space C2 has dimension 2. And so if we break it up, and it's not always the case that both of these are, that one of the two is C2, then it has to be the case that there's a scenario in which you have C2 as the direct sum of two vector spaces, each of which has dimension 1. And so if C2 is the direct sum of two vector spaces of dimension 1, you can write each of these vector spaces as the span of a particular vector. And we know that C2 contains, if we write elements of C2 in this form as vectors with respect to some basis that we've chosen here, then there must be, then one of these two things that we've broken it up into must contain elements whose second coordinate is not 0, because otherwise they wouldn't add up to the whole thing. And so what that means in particular is that there must be some element whose second coordinate is not 0 such that our subspace is given by scalar multiples of that vector. So we don't know what the second coordinate is, but we know that the second coordinate is not non-zero, and it's going to be, if we're considering the span of this vector, then without loss of generality, we can just set it to 1, and then A is going to be whatever it ends up being. Once you rescale everything. It could be 0, that's fine, but it could be something else. We don't really know at this point. All we know is that it has, say, 1 in the second coordinate. Okay? So, what does this mean? This means that, okay, so the span of this vector must be z stable. And in order for that to hold, it must be the case that for all n and z, this is what it means to be z stable. It means that for every single integer and for every single integer, acting by rho sub n on alpha is going to give us another element in the span of this vector, i.e. some constant multiple times alpha. i.e., for every single n, there exists a lambda such that rho sub n applied to alpha is that constant lambda, is alpha scaled by that constant lambda. Okay, so what does this mean? Let's write it out with matrices. We've got this matrix acting on A1 is lambda A1, and we multiply that out. So when you do the matrix multiplication, you get A plus n. 1 is lambda A lambda. So this can't hold if n is non-zero, because for this to hold, so if you let n be something that is non-zero, we have to choose lambda such that these two things are equal. Well, in the second coordinate, the only way to choose lambda is to make lambda equal to 1. But then what does that leave up here? That means that a plus n has to equal a. So that means n has to equal 0. So that never holds whenever n is non-zero. Okay, So this is a contradiction. So we assume for contradiction that rho is not indecomposable, and we got a contradiction. Therefore, it's not indecomposable. So no, it's that proves that rho is indecomposable. Okay, so here's an example of a representation which is indecomposable but not irreducible. And therefore, indecomposable does not imply irreducibility. And yeah, this completes this argument, and it completes our discussion of irreducible and indecomposable representations.